Here are the solutions to semester exam review sheet number 3. And for these problems where you are dividing rational expressions, or the same would be true if you were multiplying rational expressions, you need to do all factoring that is possible to do first. So I'm going to start with this left numerator, and that factors as the difference between two squares. So a plus b times a minus b. Below that, we can begin by factoring out a GCF of 3. And that makes it look like a squared minus 2a plus 1. And then I notice that we can do more factoring, showing this trinomial as the multiplication of two linear binomials. A minus 1 times a minus 1. And so I'm going to mark this one out. Okay, remember that when you're dividing a fraction, you need to invert this right fraction. That means flip it over, and then you change the operation to multiplication. So as I do that, I'm going to go ahead and factor. This becomes the numerator of this right fraction, and the factored form of that is a plus 1 times a minus 1. And this becomes the denominator, and the factored form here becomes GCF of 4 times the quantity a plus b. Okay, now that everything is factored and we have, for division, we always have to remember to flip the second or the right fraction. And now we look to cancel. Remember, you can cancel factors. That's the purpose for factoring. We can cancel factors either diagonally or vertically within a fraction. So let's see what matching factors we have. A minus 1, we have a plus b, and I believe that's it. So we express our answer, and if you see a problem like this on your test, you can leave your answer in factored form. Don't have to multiply all of this together, so you could save yourself a little bit of time. So a minus b times a plus 1 will be the numerator. In the denominator, I do want to go ahead and multiply 3 and 4 together to get 12 times the quantity a minus 1. And that is my answer for problem number 1. Problem number 2 is another division problem. It looks different. This is a complex fraction. So again, I want to factor everything I can. So I'm just going to come over here and I'm going to factor this numerator as x plus y times x minus y. That's the difference between two squares. The same factoring process will take place here. That's also the difference between two squares. Y plus 7 times y minus 7. Okay, well, this means division. I'm dividing by this fraction. So once again, like the previous fraction, I'm going to invert or flip this bottom fraction and show multiplication. So y plus 7 doesn't factor. However, here I can factor out negative 1, and when I do, I will make it so that it will cancel with another factor. So let's think about this. If I factor out negative 1, remember, factoring means when I multiply all this together, I still end up with this expression. It's just another way of writing this expression using multiplication. So the only way I can come up with this blue y minus x, factoring out negative 1, is if I multiply negative 1 times x, that's the negative x, and I multiply negative 1 times negative y, because negative times negative is positive. Okay, so by factoring out negative 1, I can turn this around, turn these terms around. It's still equivalent because negative 1 times x is negative x, negative 1 times negative y is positive y, but now it's written in a form where I'm able to cancel factors. So if you're like some people where you just turn this around without factoring out negative 1, you haven't created an equivalent expression. You've literally changed the problem. So I hope you see the understanding behind factoring out negative 1 here. Factoring means to rewrite this using the multiplication of two factors. Okay, so now let's cancel wherever we can. These are factors that are cancelable. Y plus 7 also. And so this answer could take on a couple of different forms. We have x plus y in the numerator. And then, of course, in the denominator, we start off with -1 times y minus 7. In your answers file, the answers slide that I provided for you earlier, I went ahead and divided -1 into both of these numerator terms. So this is how I came up with my answer, -x minus y over y minus 7. Okay, so that is the answer for number 2. Let's move on to number 3. Now we're subtracting two fractions that do not have the same denominator. So we learned years and years ago that before we can add or subtract two fractions, they have to have a common denominator. Well, to find that lowest common denominator, we need to go ahead and factor these, and that will make it easier for us to find the LCD. All right, so here's the factored form of the left denominator, GCF of 6. So I'll just mark this one out. I'm going to start with a GCF of 2 for this right side denominator. Notice how 2 is the biggest number that goes into 4, 14, and 6. So I get 2x squared minus 7x plus 3. And then I can factor more, factoring this trinomial as two linear binomials. Okay, so I can do 2x minus 1 times x minus 3. All right, so just a quick FOIL check. 2x times x is 2x squared. 2x times -3 is -6x. And then we're going to be adding -1x. And those two together gives us the middle term, -7x. And then negative times negative here is +3. It's just showing you how you can know whether the factoring that you came up with is correct. Okay, so once again, the reason for factoring is so that it makes it easy for us to find the LCD. And I'll put that in a different color. So putting all of these factors together as one common, lowest common denominator. So let's start with the numbers 2 and 6. The lowest number that both 2 and 6 would divide into evenly is 6. And then for these other binomial factors, they already share the factor x minus 3. And then I'm going to include this other factor, 2x minus 1. The LCD has to be something that both of these denominators can divide into evenly. And it's helpful if we choose the lowest, that's why we call it the LCD. We need the lowest common denominator that both of these would divide into evenly. And that eliminates the need for further reducing or factoring when we get down to the end of our problem. Okay, so here's the process. I'm going to take the red factored form of the original problem, and I'm going to divide into the green LCD. Okay, do you notice that everything, two of these cancel, 2x minus 1 doesn't cancel. So just think of multiplying 2x minus 1 times this 5 numerator, and that gives you 10x minus 5. Okay, moving over here, and the binomials are going to cancel each other. 2x minus 1 cancels with this, x minus 3. So I'm going to do 2 into 6 and get 3. And then 3 is going to multiply times this numerator, and that's 3x minus 3. Okay, now that I have common denominators, I can write this. I can go ahead and subtract. It's going to be one fraction with the common denominator as the denominator, of course. And then I'm going to combine these two numerators into one single numerator. But I got to be careful with subtraction. It's probably pretty easy. Most people would get that 10x minus 3x is 7x. But I'm afraid that a lot of people are going to say -5 minus 3 is -8. But what this says is negative 5 minus negative 3. Okay, remember subtracting negative 3 is really addition. So negative 5 plus 3 is negative 2. And so that becomes the final answer. Since I can't factor the numerator, if I could factor the numerator, it's great to do that, because then you might see other opportunities to cancel factors between the numerator and the denominator. But the numerator is prime, and so that ends up being my final answer. Okay, similar problem here, but this is addition. So once again, we need to factor. So here's the factored form of this left denominator. And then over here, this right denominator has a GCF of 2. All right, so not going to look at these anymore. We'll focus on the factored form so that we can come up with the LCD, and putting together one single denominator that is really a combination, if you want to think of it that way, of these factors. But if they already share a common factor, we don't need to list it twice. Okay, so my LCD is going to be 2, that's a factor, x plus 1, that's another factor, and then the already common shared factor, x minus 4. All right, there's our LCD. And now we begin that division process. So green, these two factors divided into these 3 factors. Everything cancels except for the 2. And 2 will be multiplied times this numerator to give us 2x minus 8. All right, over here, notice that x plus 1 will not cancel. So we're going to multiply x plus 1 times this numerator in blue. And we're going to have to use the FOIL property, because the FOIL method, because this is 2 binomials multiplied together. So that's going to give us x squared plus 2x plus 1. Okay, now we're able to do one fraction over our common denominator. And we just combine these numerators. Just think combine like terms. There's only one quadratic term. There's a couple of linear terms. 2x plus 2x is 4x. And then we have these constants. Negative 8 plus 1 makes negative 7. And that ends up being our answer for number 4. All right, on to number 5. This is a graph of what is known as inverse variation. Inverse variation, or your book calls these reciprocal functions, look like this in parent form. This would be the parent, 3 over x, and these numbers indicate a translation of that parent function. Okay, so just think about this parent function, 3 over x, make a table for it. Obviously, 0 cannot be part of the domain. We can't divide by 0, but we can divide by 1. And if we do, 3 over 1 is 3. We can divide by 3. Just pick some inputs that make the math pretty easy. 3 over 3 is 1. 6 makes it pretty easy. 3 over 6 is 1/2. Okay, and so for the parent, we have these points, and then we can also think of, don't forget, these inverse variation functions are in 2 parts. And so when you do inputs, always remember to do the opposites of those numbers. So always, or many times, I will express the table of values like this, plus minus, okay? Because if I input negative 6, I'm going to get negative 1/2. So don't forget, 2 different parts. We call these branches, 2 branches. Okay, well, let's think about how this graph is translated. Remember your translation rules. If you are adding or subtracting to x, that's going to indicate a horizontal shift. And in this case, it means 2 to the left. So for the parent function had a vertical asymptote. It always has a vertical asymptote at the y-axis. Well, if you take this graph and move it 2 to the left, that's like taking your vertical asymptote and moving it 2 to the left. So instead of having a vertical asymptote at the y-axis, we now have one at x equals -2. Okay, and then for this shift, this indicates downward since it's minus. We're going to go, instead of the parent where the horizontal asymptote was the x-axis, when we shift 5 down, it's like taking this horizontal asymptote and moving it 5 places down. All right, so here's my horizontal asymptote. And now you can think of this as your new origin. Okay, for the parent, you plotted points from here, but this whole graph has been shifted diagonally so that now the origin that we're going to plot these points from is here where these two lines cross each other. So let's just do our 2 branches. So we're going to plot the point 1, 3. We'll plot 3, 1. And we'll plot 6, 1/2. And that becomes one of our branches, just following the horizontal and the vertical asymptotes. And don't forget, we got to do the negative side. So -1, -3, -3, -1, and -6, -1/2. And that becomes the other branch. And that is your final answer. We've indicated vertical and horizontal asymptotes, and that is our answer for number 5. Number 6 is a rational function graph. It's not a translation of the parent function. The inverse variation function will always look like this. There'll be just a single constant on top, and then the variable x will be on bottom, and then you'll notice the translations. Well, notice this is not in that form. So I want you to draw a distinction between the graph from number 5, which had just a constant with x on the bottom, versus this, which is just a rational function. But there are some places, some areas, maybe points, where this function cannot go through because of that whole rule of division by 0. Well, the first thing that you should always think of when you're graphing these rational functions is factor, if possible. You should factor everything you can, if you can, and then cancel. Okay, so let's take this function and do some factoring. So in the numerator, we have the difference between 2 squares. The denominator is prime, so obviously it can't be factored. And then I notice the opportunity to cancel. I have matching factors. And so what it ends up being is it's going to be the graph of, you always will graph whatever doesn't cancel, of course, or the result of canceling. We're going to be graphing this function y equals x plus 2. That's just a linear function. It's in slope-intercept form. Y equals m, slope is 1, y-intercept is 2. But we've got this place in our line that we call a hole. And a hole is a number that if we plug that same number in for x, it creates 0 both in the denominator and the numerator. One number that does both. So just to kind of walk you through the thought process, you should be looking for vertical asymptotes. Let's start with the X-intercept. All right, the way to know if you're going to have an X-intercept is you take the numerator after canceling, set it equal to 0, and solve. Okay. When I take the numerator, the part that doesn't cancel, and I set it to 0 and solve, I get x is -2. So I know that when I graph, I'm going to be crossing the x-axis at -2. Let's go ahead and put a point there. Okay, let's look for vertical asymptotes. These are numbers that cause 0 in the denominator when we plug those numbers in for x after canceling. Well, notice I'm going to compare this function that was created after canceling. So really there is no denominator after we canceled. So therefore there's not going to be a vertical asymptote. Okay, so once again, look at your function after you're able to cancel. And if there is no variable in the denominator, then there's no way to make the denominator 0. And therefore there is no vertical asymptote. Okay, let's try for horizontal asymptotes. So you should be good at your 3 situations. If the numerator degree is larger than the denominator, there is no horizontal. If the degrees are the same, you make a fraction using the lead coefficients. And if the bottom degree is bigger, then you have a horizontal at y equals 0. Well, either way you look at it, whether you look at the original, you can see that the degree of the numerator is bigger than the denominator. Here, if you want to take it as x plus 2 over 1, which is another way of looking at this, the degree of the numerator is 1. The degree of the denominator is 0. The constants have a degree of 0. So either way you look at it, there is no horizontal asymptote. The degree of the numerator is larger than the degree of the denominator. Okay, so for oblique asymptotes, 2 things have to be true. One of them here is true. The degree of the numerator is 1 more than the denominator. But the second thing that has to also be true, you can't cancel anything. There can't be any common factors between the numerator and the denominator. Well, that is true. Therefore, we don't have an oblique asymptote. Okay, so what about a whole? I think we've already discussed that there is a number, the number 2, not only makes the denominator 0, but it also makes the numerator. And the way that you'll know, the thing that triggers a response or gives you a clue that you're going to have a whole is if you are able to cancel. If you're able to cancel between the numerator and the denominator, you are going to have a whole. And if you just look at that part that's cancelable, focus on that and notice the number that would make 0 in both of those cases. It's the same expression. But the number 2 causes 0. And so we're going to have a whole in our graph at x equals 2. It's kind of hard to know where to put that yet until I actually have something graphed. So you'll typically need to wait until you graph something, and then don't forget to go back and plug a hole in on your graph, in this case where x is 2. Okay, so now we're ready to graph. We're graphing y equals x plus 2. So y-intercept 2, slope of 1. Okay, well at this point now I'm able to see on the graph where x equals 2. This is where x equals 2, so really I could have drawn the line and then gone back and erased it, but now that I can see where x is 2 on my line, I'm just going to go ahead and insert my hole there, and then you can do dots on the other side. Alright, so we're ready to graph, and I think I'll try to do my line draw tool here just to make it nice and neat. So I'm going to do it like this, so I can do an arrow on the end. I'm going to have a line that basically it flows continuously until it gets to this point, and then it jumps. We cannot, 2 is not allowed to be an input. Therefore, this graph does not exist where x equals 2. And so that is my answer for the graph of number 6. Number 7, another rational function graph. So let's just go through our process. Just talk yourself through these points. Can you factor? And the answer is no. Nothing factors between the numerator, or in the numerator, it's prime, and the denominator, also prime. So nothing factors, so therefore I can't cancel. Remember, I can't cancel terms. I can only cancel factors. So resist the temptation to cancel with x here. These are terms, and only cancel factors, not terms. So factor no, and so therefore I'm just going to write myself a note. Canceling is not an option because there are no matching factors. Okay, well, let's look for x-intercepts. The x-intercepts will be made from taking the numerator, set it equal to 0, and solve for x. Well, taking the numerator and setting it equal to 0 and solving is going to create an imaginary number. I'm going to be doing the square root of a negative number. All right, so if you want to see it, it's going to look like this. And the square root of a negative number is not real, and x-intercepts have to be real numbers. The numbers on this x-axis, on the real number coordinate plane, they're obviously real numbers. Well, these are not real, so therefore I can't plot them. Therefore, there are no x-intercepts. So if you solve for x in the numerator and you don't come up with real numbers, you know that this graph will not cross the x-axis. All right, so now let's go to vertical asymptotes. These are numbers that cause 0 in the denominator only. So if you're not sure, just take the denominator, make it equal 0, solve for x. So it looks like we're going to have a vertical asymptote at x equals 1/2. Here's x equals 1/2. Okay, now let's check for horizontal asymptotes. This is a comparison of the degrees. The degree of the numerator is 2. The degree of the denominator is 1. Whenever the degree of the numerator is larger, that means that we will not have a horizontal asymptote. Okay, what about an oblique asymptote? Well, to be oblique, the numerator degree has to be 1 larger than the denominator. That checks. There also cannot be any matching factors that will cancel between the numerator and the denominator. That checks. So we are going to have an oblique asymptote, and how we find it is with long division. Okay, so maybe I can squeeze that in over here. Let's go ahead and do long division, 2x minus 1 into 3x squared plus, since we're skipping that linear term, I'm just going to plug in a spacer, 0x, right? So divide first term into first term, 2x into 3x squared. For some people that might be a little complicated, so if you want to pull that out, you're essentially doing 3x squared divided by 2x. So just think about it this way. The result of this would be 3 over 2x. 3 over 2x. Okay, and then multiply. So 3 over 2x times 2x gives me 3x squared. And 3 over 2x times negative 1 is negative 3 over 2x. Remember, with long division, you always subtract at this point. So the x squares cancel. And 0 minus negative 3 over 2x is positive 3 over 2x. And I'll bring down the constant. And then let's go through that one more time. 2x into 3 over 2x. So once again, this might be helpful if you just take 3 over 2x and then divide it by 2x and simplify. Well, dividing by 2 is the same thing as multiplying by 1/4. Do you notice how the x's, when you divide, will cancel? So really, we just need to show 3 over 2 times 1 over 2. And 3 over 2 times 1 over 2 is 3/4. All right, and then you can go ahead and multiply. That's going to be 3 over 2x minus 3/4. And then don't take too much time with this long division process because the remainder really is inconsequential. You don't really need it. When you reach a point, when you discover that you've got a constant here, there is no variable, notice how x is gone, and you're going to be dividing 2x into some constant. Well, since it doesn't have x involved, you can't divide 2x into just a constant, So when you reach a point where you can't divide anymore, then the result becomes your oblique asymptote. So the line that we're going to draw representing our oblique asymptote will be y equals 3 over 2x plus 3/4. All right, so let's just sketch that out. So it has a y-intercept of 3/4. I'm going to say that's right there. And then let's count out a slope of 3 over 2, up 3, right 2, up 3, right 2 again. And then I'm going to do some more points going this way. Helps me line these up with my tool. 1, 2, 3, 2. All right, and I think we're ready to draw this line. And I usually wouldn't be wrong if you didn't, but these asymptotes, I typically make them dotted. Let's see if I can line these up pretty well. Okay, that looks pretty good. All right, so we've basically sketched out ahead of time the places where we can't graph. These are areas or lines of discontinuity. One last thing we need to check for is a hole. And if we had a hole, then we would have been able to cancel factors between the numerator and the denominator. So in this case, we weren't able to do that. There's not a single number that makes both numerator and the denominator 0, so we don't have a hole to worry about. Okay, so now it's just a matter of doing inputs and outputs. So just around these oblique asymptotes, we need to know basically what happens to the left. I'm going to see what happens to the graph in between. My graph section either has to be in this area or in this area. I mean, sometimes the graph can cross over an oblique asymptote, but I'm just going to test -1 just to kind of get an idea of where the graph is going to be. Is it going to be up here in this region, or is it going to be down here? So I'm going to test -1 into the original function, and let's see what comes out. So I can just erase this to give myself a little bit more room. Okay, so input -1 looks like this, and with the calculator it should be pretty fast for you. So -1. Okay, so -1 squared is 1 times 3 is 3, so the numerator is 11, and this is -2 minus 1, which is -3. So -11/3 is the same thing as -3 and 2/3. So input -1, output -3 and 2/3. Okay, so let's see about -2. All right, so put -2 in place here. All right, -2 squared is 4. 4 times 3 is 12, plus 8 is 20. And -4 minus 1 is -5. That comes out to be nice. That's -4. So if I input -2, I get an output of -4. All right, it's starting to take shape a little bit. And now let's do a point on the other side. Let's try 0. If I input 0 for x. Okay, so it's going to be 8 over -1, which is -8. So 1, 2, 3, 4, 5, 6, 7, 8. And this really represents, as you can tell, I chose numbers on either side of -1. So -1 is, you can think of it as the highest. -1, -11/3 will be the highest point on this little graph section. And we're going to trace forever going this way. And then I'm going to hit this point and follow the vertical asymptote forever down. So that gives me one of the graph sections. And now let's see what happens on the other side of this vertical asymptote 1/2. Let's try +1. Okay, so this is 11 in the top and 1 on the bottom, 2 minus 1. So for an input of 1, you get an output of 11. And I'm just going to say that's up here. And let's try 2. Input 2. What do we get as the output? So 4, 2 squared, times 3 is 12. That's 20 over 4 minus 1, which is 3. And so that's 6 2/3. I'll say 20/3, but for graphing purposes, let's think of it as 6 2/3. So 2, 1, 2, 3, 4, 5, 6, not quite to 7. So I'm going to pretty safely say that I know I'm going to trace going up forever along that vertical asymptote, and then I'm going to trace this way to follow this oblique asymptote forever. These two pieces, typically like this, it's kind of like a hyperbola, two parabolas that open opposite each other. And that ends up being the graph. It was kind of involved, but there's a lot of things that you need to be ready to analyze, come up with before you can actually do the graph. So hopefully if you need to, you'll go back over that one again so that you can nail down all of these different thought processes. Okay, let's do inverse variation. This is actually combined variation. Z varies directly with X. Let me just write down what this means as we go. Maybe I'll color code. Z varies directly with X. Okay, that's what that means. Z and X have a direct relationship, and X is being multiplied by this constant called the constant variation. Okay, and inversely with Y. All right, so here's what that means. Inverse variation always implies division, in this case, by Y. Okay, so direct is multiplication, inverse division. And then let's follow that up. Notice the next sentence is they provided us with variable values for everything except for K. So that's a clue for you that you are supposed to find out what K is. All right, so Z is 75. Solving for K, X is 10, and Y is 5. Okay, well, you can simplify first because 10, these are factors, and you can cancel factors. 10 divided by 5 is 2, so 75 is equal to 2K. And if you divide by 2, you get 37.5 is K. So now, instead of this generic equation that matches this first sentence, given the second sentence, I now can get more specific, and I can put in the actual number for K. So that's my answer for part A. Part B is, okay, let's take the function that we were given, or that we created in part A, and let's find out what Z is if we plug in these two numbers for X and Y. Okay, so Z is going to be 37.5 times 8 divided by 6. All right, and so you might want your calculator for this one. If you multiply by 7 or by 6 on both sides, 6Z is 8 times 37.5. So 37.5 is 300. And now to solve for Z, you just divide by 6, and you should get 50. And that is your answer for part B. Okay, let's move on to number 9. This is an application, real-life application problem involving inverse variation. Notice the word varies inversely. So the volume of a gas varies inversely as its pressure. So I'm just going to take this first sentence and translate it into a math equation. It would mean volume, and inverse variation always means division into this constant that we call K. And in this case, we're dividing by pressure. Okay, so for inverse variation, if that's all you have is just pure inverse variation, K will be the numerator. And then you've got these two quantities that will vary. They have an inverse relationship with each other. And you'll be told in the problem what those two quantities are. Now, the objective is to find out exactly what number K is. And that's the purpose of this. All right, so in red, I'm going to find out what K is using 80 is V, and P is 2000. So we now know that K is 80 times 2000, and that's 16 and 1, 2, 3, 4 zeros, 160,000. Okay, so I'm going to use this now, this function, to help me come up with the final answer. Find out what V is if the pressure is 320 milliliters. So pretty easy way to come up with the answer. You just do 160,000 divided by 320. And just pulled up my calculator just to make sure. And so we got a volume of 500, and then in the context of the problem, volume is expressed in cubic centimeters. So my answer should be also in cubic centimeters. And that's the answer for number 9. Okay, number 10, this is a rational equation. So similar in a way to adding or subtracting two fractions, but when you see equals, that means you're supposed to come up with x. You're supposed to solve this. A solution is the number that we would plug in for x to make this true. And we're going to turn, the objective here is to make these denominators go away. Okay? No one likes to work with fractions. Most people don't. So the LCD is going to be our tool to get rid of these denominators. If we don't have denominators, we don't have fractions. Okay, the first thing I need to do, if necessary, is to factor. And I notice that this right side denominator can be factored. And again, it's the factoring that helps us see what the LCD is. And the LCD will be x minus 7 times x minus 6. And I'm showing it here being multiplied on both sides of this equation in order to clear these denominators. And here's how they're cleared. Because I'm going to divide x minus 7 in blue into this LCD, then these would cancel. And what's left, similar to what we did in a previous problem when we were adding and subtracting two fractions, we multiply. X minus 6 times 9, and that's 9x minus 54. Okay? And I won't go back and erase, but now I'm going to do the same thing with x minus 6. Notice how x minus 6 cancels. I'll just erase this one. Okay, so now we have x minus 7 available to multiply times 7. So I just brought down the minus sign, and now I'm going to multiply x minus 7 times 7. That's 7x minus 49. On the right side, it's nice because everything cancels, and anything divided into itself is 1, and 1 times 13 is 13. So do you notice how our denominators are gone, and we now have a pretty simple, almost Algebra 1-like equation to solve, but we got to be careful because we have this subtraction of this, really it's a binomial after we multiplied. So be careful with subtraction. Okay, now I'm going to combine like terms. 9 minus 7x is 2x. And a lot of people miss this. Negative 54 minus negative 49. Negative 54 plus 49 is negative 5. and add 5 to both sides, divide by 2. I get x equals 9. I'm going to do a quick check to make sure that 9 does not make 0 in any denominator if I replace it with x, and it does not. So it's a good answer. So that's my answer for number 10. Okay, here's a rational inequality, and it's similar, but it does have differences. First of all, you should always observe, look at your denominators. You can't factor anything, but we do have a number that if we let, in this case, a be 0, then we have division by 0, which is undefined. So right off the bat, you should identify any numbers that would replace denominator variables, just the denominator, any variables that could be replaced with numbers that cause 0, division by 0. Okay, we've spotted that. And now we're going to treat this as though it is an equation. Because eventually we're going to have the solutions to this along with 0 on a number line. And for inequalities, you test around those numbers, and you're trying to find the range of numbers. Remember, if there is a solution to an inequality, it will be a range of numbers, not just one single number. So that's what we're trying to do here, and we're going to find out any other numbers in addition to 0 that will be placed on that number line. Okay, so once again, much like the previous problem, we need the LCD, the lowest term that 3a, 4a, and 6 will divide into evenly, and that should be 12a. We're going to clear out these denominators. 3a divides into 12a 4 times. 4 times 5 is 20. 4a into 12a is 3. 3 times 3 is 9. And on this side, 6 into 12a is 2a. 2a times 5 is 10a. And when I solve for a, I get 11/10. Okay, now I know that there's only one solution to this equation. I had the previous number that caused 0 in the denominator that I have to exclude. Cannot use a as a solution. So on my number line, when I start testing, I'm going to test around 0 and 11/10, or that's another way of saying 1 and 1/10. So you just pick numbers in those areas, those 3 different sections. You can choose -1. You can choose anything you want, less than 0. You can choose +1, and you can choose +2. And we're going to plug these in to the original equation. All right. So hopefully you're good at just plug and chug. Just plug these in and see if they're true. I'm just going to do this first one, and then I'm just going to jump to the final answer just to save time because the video is getting kind of lengthy. So if I let a be -1, I get, maybe I can plug it in here. If you let a be -1, it's -5/3. If you let a be -1 again, this is going to be +3/4, negative, or minus a negative. And then our job is to see if, when we add those two together, is that result greater than 5/6. All right. So to get a common denominator, let's think of this in terms of 12ths. Okay, so we'll do a little mental math here. 3 divides into 12 4 times. 4 times -5 is -20/12. 4 goes into 12 3 times. 3 times 3 is 9/12. And 6 goes into 12 2 times. 2 times 5 is 10/12. Well, if you add these two together, that's a -11/12. Obviously, that is not greater than 10/12. So what we've concluded is that any number less than 0, -1 represents all the numbers less than 0. Since -1 didn't work, none of these work. And just for sake of time, if you try that again with 2, these are not going to work. However, if you do 1 in for A, you will get a true result. The left side will be greater. And so our answer will be all the numbers in between 0. And since we're using a as our variable, all the a's, all the numbers that fall between 0 and 11/10. And that is my answer for number 11. Okay, and then finally, to wrap this up, you need to be really knowledgeable of all the parents that we've talked about this year. And I'm just going to run through a quick sketch of these. You have these on your answer slide. The line y equals x, it's kind of hard to see here, but y equals x, of course, has a y-intercept of 0 and a slope of 1. I think I'm just going to do a rough sketch of these. So here's y equals x. The domain is all real numbers. Going along the x-axis, we're going to go forever. As x goes positive, so does y. As x goes negative, so does y. And that's going to be true going this way as well. Notice how our graph goes forever up as x goes positive and forever down. So pretty simple. The domain and the range for y equals x will be all real numbers. For the absolute value function, remember absolute value, just think of the v in value, and that'll help remind you of what this graph looks like. So let's say slope of 1, both positive and negative. And this is a rough sketch. I'm just trying to speed through this, but if you want the exact, I drew these out exactly on the answered file. If you want to go back and just look at the hard copy answers, it really should be more like this. I'm getting a little sloppy. It's not just random. You go up 1, left 1, up 1, left 1, up 1, right 1, all the way across. But you get the idea. Vertex is at the origin. So the domain here, and I'll just let this top line be domain. The domain is all real numbers for the absolute value function. However, the range is only those numbers from 0 and up. So we'll say y greater than equal to 0. This is the quadratic, so it's the U shape, and this is the parent. If you input 2, you get 4. So again, it looks something like this, the U shape. And it's the same domain and range as the absolute value. Okay. Domain, it's going to go forever, positive, negative along the x-axis. For the range, it only goes up from 0, 0 and up. So greater than equal to 0. Now, as I've said here, be ready to recognize when these are shifted or flipped. Okay, so let me just, since you're watching this, let me just give you a heads up. I might, on the exam, do something like this. The instructions will say, this is a parent, and it looks like this, roughly. All right, so you should be able to tell me that for this particular parent, it has been shifted 4 to the right, and it's been shifted 1, 2, looks like, I can't see that mark, but it looks like 3 down. I'm just going to say down 3. And it's also flipped over, so that means we would have minus in front of the parentheses. So you should be able to, based on your knowledge of the translation rules and what it means to reflect a graph, you put minus in front. In each of these cases, this would be the upside down V shape. Be ready for those translation and transformation principles. All right, number 15 is y to the third, the cubic function. So just think input 0, output 0. If you input 1, you get 1 cubed. If you do negative 1, you get negative 1 result. If you do 2, you're going to get 8. And if you do negative 2, you're going to get negative 8. So it's kind of, I guess you can kind of think of it as a skinny S shape, sort of. Okay, so the domain, of course, we can do any input we want, all real numbers, and the range, those results will be along the y-axis forever, also all real numbers. Okay, this is the square root function, so if you input 0, you get output 0, input 1, output 1. We typically say, let's choose some inputs that are perfect squares, like 4, input 4, output 2, input 9, output 3. So the square root function looks like this. The domain is not all real numbers because we can't input negatives. It's going to be, I'll just state it like this, x that are greater than or equal to 0. Okay, and that's also going to be true for the y's, because notice for this parent, the y's do not extend below 0. They go from 0, and then they're going to continue to go upward as x goes to positive infinity. Okay, the cubic, or the cube root function. If you input 0, you get output 0, input 1, output 1, input 8, I think that's 8, 2, you get output 3, and that's also true for the negative. So if you input -1, the cube root of -1 is -1, and the cube root of -8 is -2. So here's that cube root function. And the domain here, you can do the cube root of a negative number. So here its domain is all real numbers, and so is the range. And so once again, just want to throw this out. Let me just give you a for instance here. You could see something like this on your exam, where I tell you that this represents the parent that has been translated and reflected. So what's that? What is that equation? Okay, so you've moved 1, 2, 3, 4, 5 to the left. So that would be x plus 5, and you've moved 1, 2, 3 down. That's minus 3. And you notice how we've taken this parent and we've flipped it over the x-axis. And so that would require a minus sign in front of the radical. So again, just want to give you a heads up. Be prepared for looking at a graph and coming up with the equation for the transformed parent. And I think we just have one more. We looked at this earlier. This is that reciprocal function. And the parent looks like this. Obviously, we cannot input 0, and we will never get a result of 0. So for that reason, we have a vertical asymptote of y-axis and a horizontal asymptote of the x. The parent will never touch either one of these. So if we input 1, we get output 1. Input 2, you get a half. Input a half, you get 2. So you have a branch that looks like this. Again, you can't input 0, and you'll never get an output of 0. And then remember that this is in 2 branches. So if you input -1, you get -1. If you input -a half, you get -2, -2, -a half, and here's the other branch. And so you can state the domain for this as it's basically all x, such that it's all real numbers except for 0. So basically we're describing every single number except 0. And that's true for the range as well. All numbers except 0 for the y's. All right, and that concludes review number 3. A lot of stuff on this. I hope you're preparing well. And as you prepare, if you have any questions, let me know.